Okay, well, we are back, and I'm going to try and make the case that we need to study psychology scientifically. I always like to ask my classes in person to think about what differentiates philosophy from science. Obviously, we can't have a give and take here, but think about that. How philosophy differs from science. Philosophy relies really heavily on logic to explain things. You can prove something in philosophy by making an argument that others can't break down. If your argument stands up to other people's attempt to refute it, then you've proven your point in philosophy. I'm emphasizing proven because in science we don't really use the word proven. In science, we collect data and we test hypotheses. And you either support the hypothesis or you refute it. You do not prove it. In science, we rely on data. Now, why do we do that? Well, first off, our logic, or our intuition, as it used to be called in the olden days, is not very sound. I mean, we have to really work hard to suspend a lot of thinking errors if we want to actually be able to explain information correctly. Our common sense is a little shaky. I mean, the things we know are not necessarily true. We know a lot of things that aren't true, but we don't know that they're not true. We don't know that it's faulty information. So I have a couple of things that might help to illustrate this. And unfortunately, this is another one of those things that's really tough to do without a group and things like this. So if you're interested in what I'm saying to you and you want to know whether what I'm saying is accurate, this is a really fun thing to do to your friends and family. Just test them on this design. Do 10 trials per person and then add up your results and see if what I'm saying isn't accurate. I recommend that if you're going to do it, though, you need to do at least 5 different people using at least 10 trials per person, because you might get very unusual, things can happen over the short run that wouldn't happen over the long run. So it's important to do lots of different trials. All right, so here's the premise. It's a lot like playing Let's Make a Deal. I've got 3 envelopes. One of them contains a fake $100 bill. Well, I mean, it has a $100 bill, but we're just pretending. So that's why I mean fake. So we're pretending like one of these holds a $100 bill. The job of your participant is to say which envelope they want. Your job as the researcher is to make this little table and record everything that happens, right? So when you make this table, you're going to set it up for 10 trials per participant. You're going to randomly assign a correct letter for each of the 10 trials, and the choices are A, B, and C. Like she got the 3 envelopes. A, B, or C for each of the 10 trials. When you're working with your participant, of course, do not let them see this table, because it's a lot easier to guess the letters when you've seen them. So don't let them see your table. And then as you're doing the experiment with the participant, ask them, which envelope do you want, A, B, or C? And they'll make their choice, and you write it down. Let's say my subject chose B. And you go, well, I can tell you the correct answer isn't C. See how I didn't eliminate the actual correct answer, and I didn't eliminate what the participant said. So I can tell you it's not C. Do you want to stay or switch? Probably they'll say stay, because that's what people like to do, because they're like, I have no reason not to. So they'll say they'll stay. And then you say, you lose, and make sure you write all this down, because you'll lose track of it later. So write it all down on your little table. You say, you lose. Do you want to pick A, B, or C? Go immediately to the next trial. So they're a little bit confused. Let's say that again they pick B. Now I have to be a decent actor, because I could say A or I could say C is not the right answer. I could do either one, but I don't want them to realize they'd actually said the right answer, and that I'm trying to have to make something up really quickly. So you'd have to say, okay, well, I can tell you that the correct answer is not A. Would you like to stay or switch? Well, they lost on the last day, so my fake participant decided to switch this time. You lose. you want to pick A, B, or C? And you keep going like that without giving them any other feedback till you've done 10 trials. When you get done, I'll just warn you right now that you don't just look at how many they got right and how many they got wrong. You want to count up how many times overall they stayed, use that as the denominator, count up the total number of times they won when they stayed, and use that as the numerator. And that'll give you a proportion of wins per stays, right? And then do the same thing for the switches. Count up how many times they switched, count up how many times they won when they switched, and see what their proportions are. More than likely, their proportion of wins will be much higher when they switch than when they stay. I think what I'll do is link in our classroom an activity where you can actually practice this just by yourself. And so if you don't feel like collecting data and having fun, you could do it just by yourself. And you'll see that usually the proportion is about 60% wins when switched and about 30% wins when stayed. Now please note those two things don't have to add up to 100 because each of them are being calculated independently. So you have wins when stayed could be 100%, wins when switched could be 100%, right? So those are independent things. Here's the thing. Why would it possibly matter whether you stay or switch? That's what we're testing here. Does it matter if you stay or switch? I'll tell you the philosophical, logical, mathematical, that's getting a little sciencey, explanation. But if you're like me, it's still going to be unbelievable, and you're going to have to test it yourself to find out whether what I'm telling you is true or not. So here's the thing. Let's go back to this slide real quick. Sorry. There we go. When you're picking an envelope initially, I think we can all agree that all those envelopes have a 33% chance of containing my $100 bill. So when I pick an envelope initially, they all have the same chance. So if I pick B, let's say, it has a 33% chance of being right and a 66% chance of being wrong. Now let's say that I picked B, so the person who was collecting data said to me, I can tell you it's not C. Do you want to stay or switch? I'm thinking to myself, as a naive participant, what's the difference? There's a 50% chance that A is right and a 50% chance that B is right. What's the difference? I'll stick with what I picked. That's where logic is faulty. Because when I picked B, it had a 33% chance of being right and a 66% chance of being wrong. So that means if I switch, I should be doubling my odds of winning because I switched from an object that had a 33% chance of being right to the only remaining object that had been under the 66% probability. So I should double my chances. And as I said, in my classes, it almost always comes out 60% for the switches and 30% for the stays. I've been doing this demonstration for a really long time. I've got a lot of data. Switching is the better strategy. And the best way I can explain it is that B has a 33% chance of being right and a 66% chance of being wrong when I pick it. And that 66% is still in play after one of the envelopes has been eliminated. The best way to understand it is to do it yourself. So you can either play it with a friend using the design I mentioned, or like I said, I'll link it in the classroom so you can play by yourself. The basic premise, though, is that I could have spent years thinking about this problem and never come to the conclusion that it matters if you stay or switch. I never would have come up with that because my logic is too limited in that capacity. Most of us, given something that's happening out in the world, when we try to explain it, why did that thing happen? I'm going to grab the first thing that I can think of that sort of kind of explains it. And I'm probably going to be partially right to probably entirely wrong. Logic is limited. Have you ever heard the old phrase, absence makes the heart grow fonder? Have you also heard the phrase out of sight, out of mind? These are called aphorisms. And they're called aphorisms because they're just, it's another way of saying truisms. They're both true, right? No, how can they both be true? They're opposite of each other. Seek and you shall find. You should be bold. You are not going to find it unless you seek it. But curiosity killed the cat. Don't be too bold, right? Bad things will happen to you. The pen is mightier than the sword. Actions speak louder than words. How do we have so many opposing aphorisms? How can that be? Well, it's partly because aphorisms are usually invoked in hindsight. So your friend has their romantic partner. They're all, passionately hot and heavy for each other. We love each other, blah, blah. But one of them goes away for some reason, goes in the military, goes off to school, goes away for a little while. And when they come back, they're even stronger than they were before. And you say, well, of course they are. Absence makes the heart grow fonder. Or they break up. And you go, well, what do you expect? Out of sight, out of mind, right? Aphorisms are awesome because in hindsight, we can explain anything. Everything makes sense in hindsight. So our tendency to think we could have predicted something before it happened, when in fact we only know how it worked out after it happened, right, is what we call the hindsight bias. So when something surprising happens, very quickly afterwards, we'll say, I knew it. I knew that's what was going to happen. I don't want to reveal what team is my favorite. Later I will reveal it, but I still want you guys to like me and stuff right now, so I won't take a partisan stance on football teams. But let's just say my team had been in the Super Bowl 3 times and gotten just killed. Oh, they were horrible, and it was embarrassing to be their fan. They were just so horrible. So they made it back to the Super Bowl, and I thought about not watching because I didn't want to watch it again. The horror, the just horrible, no. And then I thought, well, I'll watch it, but I'm not going to wear any of my shirt or anything like that because I'll probably jinx them. Good scientific thinking. And as the game was starting, they were the favored team. They were predicted to win. And I was like, you guys, your announcers, stop saying that. You're going to cause them to lose, right? My team doesn't win the Super Bowl. Stop saying that. The whole game, I kept thinking, man, we're ahead. I know they're going to come out after halftime and we're going to lose because every time we're ahead before halftime, we end up losing. Well, we're ahead in the fourth quarter. I can't tell you how many times we've snatched defeat out of the jaws of victory. I know we're going to blow it in the fourth quarter. It ticks down, 6 seconds left, and the other team has the ball. They do the Hail Mary. They don't score. My team has won. I am not even moments later going, I knew it. I knew they could win. That is hindsight bias. I did not know it. I completely just denied all of it, that it was even possible. I could not have shown any more that I did not believe my team could win. But instantaneously after the event happened, I started saying a hindsight biased interpretation of what had just happened. It's really common. A lot of aphorisms give us the opportunity to pull something out and say, see, because absence makes the heart grow fonder. Of course that it worked out for this couple, right? We overestimate our ability to have predicted something before we knew its outcome. After the outcome, we're like, oh, I could have told you that's what was going to happen. Psychology is particularly a target of this kind of logic. You hear the results of a psychological study, and a lot of times you're like, why'd they even bother? I could have told them that. Everybody knows that. Well, probably everybody doesn't know it, or the scientists wouldn't have been compelled to do the study. Probably there was actually some question about what was going to happen, or they wouldn't have done the study. So this tendency to think we could have explained something, now that we know how it worked out, can undermine the accuracy of our actual interpretations of behavior and mental processes. What we need to do, instead of explaining a behavior after it happens, is we need to predict what's going to happen. We need to state a hypothesis, predict what's going to happen, and then see whether that's what actually ends up happening. So we have to, in science, actually deliberately suspend our tendency towards the hindsight bias. Overconfidence. Us humans tend to think that what we know is correct, whether it really is or not. Even if there's a whole bunch of information that we're wrong, we'll still stubbornly cling to the belief that we're correct. So in everyday life, that's probably not a huge problem. Maybe we annoy our friends and family because we stubbornly say we know something. Google's made that a little harder to do lately, though, because, if you have a dispute over what's true, people will Google it, and that settles the dispute pretty quickly. Back in the olden days, you couldn't just whip something out and prove that you're right. And so people would just get intractable, and they'd say, I know what happened. I know what's right. This is the correct interpretation. And we can be pretty confident when we are very incorrect. Here's an example of overconfidence in, explaining why I'm engaging in this behavior. He says, I know the last 5 scratch-off tickets didn't win, which means the next one must be a winner, right? Like, that is such faulty logic. But he's confident. He's overconfident. He's going to waste his money, probably going to lose again, overconfident. I'm going to put this estimation quiz in the classroom also, because it's a really great way to, in the Canvas classroom. This really illustrates the tendency to believe we know more than we really do. So I don't want to ruin the little quiz for you. It's just for fun. You can share it with your friends if you want. Another faulty thinking problem that is rectified by science is that we humans have brains that are designed to try and figure out what's related to what out in the world, what caused what, what's likely to cause something else, those kinds of things. We perceive order where there really is none. If you were playing gin rummy, which of these hands do you think is more likely to be dealt to you? And I picked gin rummy as my example because gin rummy likes a hand that looks like the one on the left, right? Like, you want that one on the left. Can you imagine if you got dealt that hand while you're playing rummy? Everybody else would think you had fake cards in your pocket or something, that you got that beautiful, run of numbers in the same suit. But if you think about what I asked, which hand are you more likely to be dealt? Truth is, you're equally likely to be dealt either one of these two hands, because the likelihood of a 10, Jack, Queen, King, Ace of hearts is just as likely as a 6 of hearts, and an 8 of clubs, and 5 of clubs, a 3 of diamonds, and a 9 of spades. But if you're like me, when you look at these two hands, you see one I want and junk, and you didn't really think, what's the likelihood of that specific arrangement of junk? You thought, well, the likelihood of a royal flush is really small, and the likelihood of junk is really high. So I'm going to say, I'm more likely to get the hand of junk. One way to think about it is, imagine if instead of the game being that I want those cards that are all in the same suit and all, in ascending order, what if I want a hand, like, you get points in my game if you can get all 4 different suits represented in your hand, and all the numbers in your hand are different numbers. Now suddenly the one on the right, you're like, oh, well, that's the one I want. What's the likelihood I'd get that? Oh, yeah, that makes more sense. The probability is the same, but because the one on the left looks orderly, we think that it's harder to get that arrangement. Okay, I've been collecting things that have come to me via email or Facebook memes, things like that, over the past 25 years. So some of these are older than others. To try and illustrate how people will send these things around saying, wow, this is amazing that this thing happened. Wow, isn't this amazing? But you know what? If there are a lot of things happening in the world, some are going to look orderly. So, for example, right after 9/11, an email went around that showed you that if you folded the $20 bill in a particular way, you ended up with what looks like the Pentagon burning in one folding orientation. If you flip it over, it looks like the Twin Towers burning. Wow, in fact, the email ended with, what are the odds that a simple geometric folding of the $20 bill would accidentally contain a representation of both terror attacks? it was supposed to be some kind of Nostradamus style predictive. They designed the $20 bill somehow knowing that it would be relevant in the future. I'd like to point out that those things only look like what they're purported to be because of context. I mean, if you folded your $20 bill prior to 9/11 in these orientations, I don't think you would have said, this looks like the Twin Towers burning. But once it became relevant, oh my gosh, it looked like it was predictive, like somehow it was a foreshadowing. This one went around recently. It's supposedly, I've seen it on the internet a couple of times. It's supposed to be the crane is hanging the moon. Like, wow, that's amazing. Except for it was produced, given a clear day, it would look like this every 28 days, right? So it's like, not that amazing. How about this one? Brothers from another mother, right? Oh, they got the same fur pattern. A lot of animals have that same fur pattern, don't they? It's a really common animal fur pattern. You see it on goats, you see it on all sorts of creatures. But putting them next to each other, suddenly it looks like it's amazing. It was preordained. It was not random. Got to be careful about that stuff. So how can we be a little bit more scientific? Okay. This picture illustrates the concept of an aura. Some of you may be familiar with auras. It's energy that supposedly surrounds us, and some people can see them, supposedly. So, can they? Can some people see auras? Well, we can test this scientifically. Okay, so supposedly she has this energy that's surrounding her. As you could tell, it's a photoshopped energy in this picture because, I guess cameras can't see auras, so we had to make one. Can some people see auras? Well, James Randi, who's a big skeptic, he used to be a magician, and now he's trying to convince people to stop being such suckers, as he likes to say. He developed a testable prediction to determine whether some people can see auras. He said, if you can see the aura, you shouldn't have to see the person's body in order to see the aura. So he built a screen, kind of like this black rectangle, and sometimes there was a person behind the screen, and sometimes there wasn't. And then he got people who said that they could see auras, and he asked them, can you see an aura? They didn't do any better than chance. Those of us who claim not to be able to see auras would do just as well as the people who said that they could see auras. So we asked a scientific question and figured out a way to test whether a person can do this, psychic kind of phenomenon. So let's wrap up here with just like some tips on how to think scientifically, how to adopt a scientific attitude. First off, you need to be curious. I have to say it's the thing that probably annoys my family the most, but solidifies in my mind that I probably should have gotten a PhD in psychology, is that I ask questions about everything. I want to know all the time, what is going on? Why is that person doing that? Why is this like this? So I'm just full of curiosity. What is this? Always asking new questions. You really can't do much science if you run out of questions, right? So here's a picture of a woman eating lunch at her desk while looking at her computer. Something as mundane as that could generate, I pulled that off the internet. I came up with I Googled, I think, daily activity or something, and I just found this on the internet. And then I made up some questions. Is eating at one's desk common to all employees? Does everybody do that? Is it more common when a person is under stress? Is it something that women do more than men do? I don't know, right? Those are the top three things that just popped into my mind. When you're curious, you can generate questions about a lot of things. Skepticism, though, needs to kick in, right? Where you say, okay, let me see your facts. Where did you get that information, right? So this is actually a two-part definition. Not accepting a quote-unquote fact as true without challenging it. And then the second part is attempting to falsify facts. That's a really important aspect of science, is when there is a claim that we know the answer to something, the first thing a good scientist should do is say, well, let's test that. Let's see if we can show you that you're wrong. So, for example, if I made the claim that all swans are white, the first thing that a good skeptic will do is say, okay, let's find a non-white swan. Let's look for a non-white swan. I don't believe your claim. Let's look. So when we see that nobody could see the aura, we shouldn't say see, because psychics are always just faking it. That's not what we should do. We should say, okay, so nobody could see it. Is there some other explanation for why no one could see it? Most importantly for science, we say, did I set up the experiment correctly? So maybe the rectangle that they were standing behind was too big so that it would have actually even included the aura behind it, right? Maybe it was too small and they were able to see something that was behind the screen and they interpreted it as evidence that a person was back there or something. And they weren't really seeing auras, but they were giving incorrect information because they thought they could tell whether a person was back there. So even if they thought they were seeing an aura, they're like, well, but I'm not sure. I don't think there's anybody back there because the screen's so small. Is there a problem with how I set it up? I'm just making up possible interpretations because you have to always be thinking those thoughts. What did I do that might have facilitated an outcome that I wanted that is actually not an accurate outcome? So we need to be not only skeptical about other people's claims as scientific thinkers, but we also have to be skeptical of our own conclusions. Like, have I seen it wrong? Have I done it wrong? Humility. Oh, you got to be humble to be a scientist. I'll tell you that. But to adopt a scientific attitude, you need to be humble also. The goal in science is to find the truth. It's not to be right. Scientists who are motivated by being right are what we call junk scientists. They are not displaying actual science. They have an agenda, and that's not good science. So let's say that we put somebody behind the rectangle and their aura was visible. Like, let's say we had a person in here who says that they can see auras, and they are actually, every time there is a person back there, they say, I see an aura, and every time there is not a person back there, they say they didn't see an aura. And we're like, holy cow, it looks like this person's actually seeing auras. Scientists would say, okay, maybe we're wrong. Maybe there is such a thing called an aura. They wouldn't say, okay, nope, I firmly believe that you are making it up somehow. No amount of evidence would ever prove to me that you can see auras. Scientists don't do that. When there's irrefutable evidence, then you have to say, I guess I was wrong, right? You also have to be humble enough to recognize that you may have done something wrong in your design and come to the wrong conclusion too. So you have to admit your own mistakes. So science is not for the faint-hearted, that's for sure. All right. I'm going to stop here so you guys can take a break, and then we will come back and we will finish up this chapter by discussing the different research methods that we use in psychology.